All right, let's dive into something pretty cool today, huh? Iterated sumsets. Sounds kind of technical, I know, but trust me, it gets really interesting.
Definitely.
You give us this paper, Relative Sizes of Iterated Sumsets, by Noah Kravitz, and it's packed with surprises about how sets of numbers grow when you keep adding them to themselves over and over.
It's amazing how a concept that seems simple on the surface, like adding sets, can actually have so much depth.
Right. And the paper jumps right into this question asked by a mathematician, Melvyn Nathanson,
Yeah.
about, how these sizes of the sumsets, how they compare.
Yeah.
So, okay, for our listener, let's try to make Nathanson's question a little clearer.
Yeah.
Imagine we have two sets of numbers, call them A and B,
Mm.
and you add the numbers in A to themselves, like 1 plus 2 plus 3, then another 1 plus 2 plus 3, and so on. That gives you a new set, right?
Right.
We call that the sumset of A. Do the same with set B. Now, say the sumset of A is smaller than B's sumset after you do this addition thing once. Nathanson's like, hold on, what happens if we do this a bunch of times? Add the sets to themselves again and again. Could B's sumset suddenly become smaller than A's? And could they, switch back and forth, bigger, smaller, as we keep going?
It's really a fascinating question. You'd think that intuitively the set that's bigger after one round would just kind of stay bigger.
Right, exactly.
But it turns out that's not always how it goes.
That's what makes it so cool.
Yeah.
And Kravitz in this paper, he doesn't just find a few examples where it happens. No. He proves a whole theorem about it. Theorem 1.1, to be precise.
Yeah. Theorem 1.1 is like a big aha moment. It says essentially that you can take any number of sets, 2, 3, 100, whatever, and no matter how many times you add them to themselves, you can arrange those sets so the sizes, as you keep making those sumsets, they can change in any order you want.
Oh, wow.
Like literally any order. It's wild.
So it's like, imagine a horse race. But instead of horses, we've got these growing sets, right? And what's crazy is you can basically rig the race so that any horse can win, and they can even switch places a bunch of times while they're running.
Yeah. That's a perfect way to put it. It's so counterintuitive. You wouldn't think you could have that much control over how these sets grow just by choosing the sets themselves.
Right. So the next question is, how does Kravitz actually prove this?
Right.
He's got to have some tricks up his sleeve, and one of them is these things called homogeneous arithmetic progressions.
Yeah, those are key. Think of them like the building blocks for the sets that he creates to prove this theorem.
Okay.
There are sequences where the difference between the numbers is always the same, like 1, 4, 7, 10. And that lets him be very precise about how the sizes of the sumsets change as he adds the sets together.
So it's like he's picking out specific ingredients, and he knows exactly how they'll affect the final result.
Exactly. And a big part of it is how he arranges these progressions, particularly the spacing between them. That's what creates those surprising shifts in the race we were talking about.
Got it. Now, to keep track of the size of these growing sumsets, Kravitz introduces this idea of scales, and he groups them together into what he calls clumps.
Yeah. So these scales, they're like markers for how much the sets are expanding at each step.
Okay.
And lemma 2.3 in the paper, it basically gives you a way to estimate the size of the sumset based on how these scales are clumped together. It's like saying, okay, if you have this many scales in this clump and that many in that clump, then your sumset is going to be roughly this big.
I see. So the arrangement of these scales, it's like a blueprint for how the sumset is going to grow.
Exactly.
Pretty cool. So we've got these progressions, these scales, these clumps. It's all starting to come together.
It is.
But the real genius, the real magic trick here is how Kravitz picks the starting points for these progressions and the spacing between the numbers in them.
Absolutely. That's where things get really, really clever. He basically figures out how to tune these progressions so that he can make the sets grow in absolutely any order he wants. And he lays that out in Proposition 2.4.
So if lemma 2.3 is like the recipe, Proposition 2.4 is him saying, all right, here's how to adjust the ingredients so you get exactly what you're aiming for.
Yeah, that's a great way to put it. It's all about control, about finding the precise settings that will make these sets behave exactly how you want them to.
Amazing.
Yeah.
Okay, so to really get into the nitty-gritty of how he does that, we're going to have to dive into the specifics of those progressions and how they're constructed.
Definitely. We're just getting started. To really grasp the brilliance of what Kravitz does, we need to dig into how he uses these homogeneous arithmetic progressions. Remember, he's trying to prove Proposition 2.4, which says he can arrange these scales so the sumsets grow in any order we want.
Right. So it's not enough to just have the clumps. He has to arrange the scales within those clumps in a very specific way. How does he do that?
He defines a sequence of scales. He uses this notation, alphac, II, where spec tells you which set you're looking at, and I is like the index for the scales within that set.
Okay.
And he builds these scales using, well, a kind of clever combination of things. You mentioned generalized arithmetic progressions, right? Uses those. And also this sequence of parameters that grow really, really fast. He calls them gamma.
Okay, I can follow so far. I get regular arithmetic progressions, where you add the same number each time to get the next term. But what's a generalized one?
So in a generalized arithmetic progression, instead of adding a constant difference, you add a sequence of differences.
Yeah.
Like instead of 1, 3, 5, 7, where you always add 2, you might have 1, 4, 8, 15, where the differences are 3, 4, and 7. They can change.
Oh, I see. So the spacing between the numbers can vary, and how do those gamma things, the ones that grow fast, how do they fit in?
Those gamma values, they're super important for controlling the spacing between the scales, and that's what determines how those clumps form, remember. Scales are in the same clump if they're like close enough together, and close enough means they differ by less than gamma at a 1 month. So by making those gamma values get big really fast, Kravitz makes sure those clumps form in a very specific way as we go through the steps of making these iterated sumsets.
Oh, it's like he's using those fast-growing numbers to kind of fine-tune how the scales get grouped together.
Yeah.
The bigger gamma gets, the stricter our definition of close becomes, right?
Exactly. And now let's look at how those alphac I scales themselves are actually constructed. It gets a little technical, but bear with me. It's worth seeing how it works.
Yeah, for sure.
Okay, so each scale, alphac I, is defined like this. Alphac I, and our I die. Where M is this big fixed number that we choose, it's a scaling factor. Then you've got surrogate I dollar, which is an integer. It tells you where that scale is within these generalized arithmetic progressions. And then there's null I dollar, another positive integer. It makes sure the scales within each clump are spread out the right way.
Okay, a lot going on there. Can we break that down a bit? Like, what's each part doing? How do they all work together to control those sumsets?
Of course. Let's start with M, that scaling factor. It's got to be a big number, and it makes sure the scales are far enough apart from each other. The bigger M is, the bigger the gaps between the scales get, and that helps to make those separate, distinct clumps.
So, like, M is kind of setting the overall zoom level of our construction.
Exactly. Now, things get interesting with RAKI dollar. Those integers, they decide which generalized arithmetic progression a scale belongs to. And the way Kravitz picks those RIK values, that's the key to making the sumsets grow in the order he wants.
I see. So if we want one set to be bigger than another at a certain point, we got to put the right scales and the right progressions, yeah.
Exactly, you got it. And then we have non-K. These are like little adjustments, making sure the scales within each clump are spaced out just right. Like they keep the scales from being too close, because if they get too cozy, the clumps might merge and mess up the whole growth pattern.
So they're like making sure everyone stays in their lane, keeps the clumps neat and tidy.
Yeah, exactly. Now, to really get this, we need to look at how those Torquay values are chosen. That's where Kravitz's genius really shines through.
All right, lay it on me. What's the secret to these Torquay values?
Okay, remember those gamma values we were talking about before?
Yeah, the ones that grow super fast.
Right, they come in here too. Kravitz picks the Torquay values so that the differences between them are either really tiny, like less than gamma LO1, or really big, at least gamma plus 2, 2.
Wait, hold on. Those gamma values, they also determine which scales are in the same clump, right?
You got it. That's not a coincidence. See, by choosing the values based on those gamma values, Kravitz makes sure the scales in the same clump are close together, but scales in different clumps are far apart. This keeps those clumps well-defined and separate, which is super important for that lemma 2.3 we talked about.
Oh, wow. So he's using those gamma values to kind of guide everything, both how the clumps form and how the scales are arranged within the clumps.
Exactly. It's all connected. And that's how he gets this incredible control over how those sumsets grow. By choosing the right RK values, he can tweak the size and arrangement of the clumps, and that lets him control the overall size of the sumsets at each step.
It's like he's conducting this whole orchestra of numbers, right?
Yes, a perfect analogy. And the amazing part is he proves that he can make them play any tune he wants. No matter how you want those sets to grow and change places, Kravitz can find a set of RK values that'll make it happen. It's incredible.
So, okay, we've got these scales, the alphas things, built from those generalized arithmetic progressions with all these carefully chosen parameters, right?
Right.
And we've got the clumps, which depend on those gamma values. But I'm still trying to wrap my head around how it all fits together to actually prove proposition 2.4. Remember, that's the one that says Kravitz can find a set of scales that'll make those sumsets grow in any order we want.
Yeah, that's where it all comes together. The proof of proposition 2.4, it's where all these pieces we've been talking about, they kind of click into place. It's a pretty clever argument, uses the properties of those progressions, how the scales are arranged in the clumps, and those estimates we get from lemma 2.3.
Okay, break it down for me. Like, where do you even start with a proof like this?
Well, it's a proof by induction, right? So
Yeah.
you start with the base case. In this case, it's when h equals 1, meaning we're only looking at the original sets, not the sumsets yet. Kravitz shows that even at this first step, he can arrange the scales so the sets have the sizes we want them to have.
So he sets up the starting line of our race, just how we want it.
Exactly. Then comes the inductive step, and this is where it gets a bit more tricky.
Okay.
We assume proposition 2.4 is true for some number of times we've added the sets. So we're assuming we can make the sets grow in any order we want up to that point. And then we got to show it's also true for h plus 1, meaning we can keep that control going for the next step.
So it's like, okay, assuming we can control things up to a certain point, can we prove we can control what happens next?
Right, exactly. And to do that, Kravitz uses that special structure he built into the sets with the progressions and the scales. He shows that by adjusting the parameters of those progressions, like where they start and the differences between the numbers, he can change the size and arrangement of the clumps that form at that h plus 1 stage.
So he's like fine-tuning those progressions to keep the sets growing in the right order.
Exactly. By making those little tweaks, he keeps the differences between scales small within a clump and large between different clumps.
Right.
And that, together with lemma 2.3, lets him control the relative sizes of the sumsets at that next step, making sure they match the order we want.
Wow, so it's like a chess game. He's always thinking a few moves ahead.
Haha, yeah. And that's the beauty of induction, right? You start with a base case, then you show you can build on that step by step to get where you want to go.
Okay, so he proves proposition 2.4 with induction, showing he can arrange the scales to get any order of growth for the sumsets. But how does that connect back to theorem 1.1, the main result of the paper?
Good question. Proposition 2.4, it's a big stepping stone to proving theorem 1.1. Remember, that theorem says that for any bunch of sets and any order you want for their sumsets, you can arrange those sets to make it happen.
Right. So the theorem is the big picture statement about how unpredictable these sumsets are, and proposition 2.4 is like the tool he uses to make it all work.
Exactly. The proof of theorem 1.1 uses proposition 2.4 in a really smart way. You start with any sets and any order you want for their sumsets. Then you use proposition 2.4 to find a set of scales that, when you use them to build these things called dilated intervals, they'll give you sumsets that grow in that exact order.
Okay.
Then all you got to do is find a way to connect those scales back to the original sets you started with.
So like you use proposition 2.4 to make a perfect set of sumsets, then you figure out how to translate that back to the original sets.
Yeah, exactly. To do that translation, Kravitz uses this really clever mapping between the scales and the elements of the original sets. It's like he makes sure the cool behavior of those perfect sumsets carries over to the original ones.
Wow. It's like he's embedding that unpredictability right into the original sets.
Yes, and that's it. That's how he finishes the proof. He combines proposition 2.4 with this mapping technique, and boom, theorem 1.1 is proven. He shows that the world of these sumsets is way more chaotic and unpredictable than we might think.
It really is mind-blowing. Something as simple as adding sets together, and it leads to this whole world of complexity.
It is. It just shows the power of math, how you can start with something simple and find these amazing hidden patterns.
This has been such a fascinating deep dive. Thanks for taking us through all the details of Kravitz's work. It's really changed my perspective on how these iterated sumsets work.
I'm glad you enjoyed it. And who knows what other discoveries are out there waiting to be made in this field. Maybe one of our listeners will be inspired to explore it even further.
That'd be fantastic. So to all our listeners out there, keep exploring, keep asking questions, and never stop being curious about math. There's always something new to learn.
Absolutely. And remember, the best way to learn math is together. Share your ideas, work with others, and let's keep unraveling the mysteries of the mathematical universe.
Couldn't have said it better myself. Thanks for joining us on this deep dive, everyone. We'll see you next time. Welcome back, everyone. Today's deep dive is going to be a wild ride. Buckle up. We're going deep into the world of iterated sumsets and just how weird their relative sizes can get. Someone said in this paper, Relative Sizes of Iterated Sumsets by Noah Kravitz.
Oh yeah, Kravitz's work on sumsets is really interesting.
And it all starts with this question posed by Melvyn Nathanson. He basically asks, can the relative sizes of these sumsets actually flip-flop as you keep adding more and more elements?
Yeah, it's a deceptively simple question. Like you think, oh, adding sets, how complicated can that be?
Right. But it turns out it leads to some really mind-bending math. And, spoiler alert, Kravitz actually manages to construct sets that do exactly that.
He shows that this flip-flopping behavior is totally possible. Pretty cool, huh?
Definitely.
Yeah.
But, okay, before we get too far ahead of ourselves, let's take a step back. Remind everyone what we're talking about here with sumsets.
Sure.
Like at the most basic level.
Okay, so imagine you have a set. We'll call it A. When we talk about adding a set to itself, we're not just adding up all the numbers inside.
Right. That would be way too easy.
We're talking about Minkowski sums. So you take every possible combination of adding one element from A to another element from A.
Gotcha. So if A is, say, the set 1, 2, 3, then 2A, the twofold sumset, would be...
2A would be every possible sum you can get by adding two elements from A, possibly the same element twice. So you'd have 1 plus 1, 1 plus 2, 1 plus 3, 2 plus 1, and so on.
Okay, I see. And we can keep going. 3A, 4A, these are what we call iterated sumsets. And now the million-dollar question, Nathanson's question, is this. Suppose you have two sets, A and B. Could it be that for some number of iterations, say 5A is smaller than 5B, but then later on, like 10A is actually bigger than 10B?
Exactly. Can that relative size, can it actually reverse like that? And Kravitz's work dives into this question.
Okay, so that's the setup, but I have to admit, when I first glanced at the paper, the notation looked a bit intimidating. We've got eightfold sumsets, which are written HA. Then there's the Minkowski sum, which is A plus B. And we also have dilations like U dot A.
I know what you mean. The notation can be a bit dense, but it's really just a shorthand way to represent these operations concisely. Don't let it scare you off.
Okay, good, because I definitely don't want to get lost in the symbols. So maybe we could break it down for our listeners a bit.
Sure. When you see HA, just think of it as adding the set A to itself H times. A plus B, the Minkowski sum, means you're creating a new set by taking all possible sums of an element from A and an element from B. And when you see E.A, just think of it as multiplying every single element in set A by the number.
Okay, that actually helps a lot. Thanks for clearing that up. So with the notation demystified, let's dive into the heart of the paper, which seems to be lemma 2.3. This lemma gives us an estimate for the size of these h-fold iterated sumsets. And to do that, it uses this really clever construction of a specific set A.
Right. And the way Kravitz constructs this set A is super interesting. He uses a union of dilated arithmetic progressions.
Okay, hold on. Dilated arithmetic progressions. I think I need a visual here. What are we talking about?
Imagine taking several number lines and stretching them out by different factors, then kind of weaving them together. Those stretched out number lines are like your dilated arithmetic progressions, and the whole thing combined is your set A.
All right, I'm starting to picture it. So each of these progressions is stretched by a different amount.
Exactly. And the amount we stretch them by is determined by what Kravitz calls the scales, denoted by psi. And there's also this other important parameter, the width parameter, that might seem like a small detail, but it actually plays a big role in controlling how these different scales interact with each other.
Okay, now you've got me really curious about this width parameter. What does it do exactly?
So think of it like this. If two scales are close together, like closer than this width parameter, they get grouped together. It's kind of like sorting beads of different sizes using a sieve. Scales that are close enough fall through the sieve together.
That makes sense. So the width parameter determines which scales get lumped together into the same group.
Right. And then the really cool thing is that lemma 2.3 basically tells us that the size of the entire h-fold sumset is essentially determined by the differences between the largest and smallest scales within each of these groups.
Well, wait a minute. Are you saying the size of the whole sumset boils down to these little differences within each group of scales?
Pretty much, yeah. It's like all the complexity gets distilled down to those key differences.
That's pretty remarkable. So we've got these groups of scales, each with its own range of values, and those ranges dictate the overall size of the sumset.
Exactly. And that's where things start to get really interesting, because now we can manipulate those groups and therefore the size of the sumset just by tweaking the scales and the width parameter.
Okay, you've definitely piqued my curiosity. So how does this all tie back to Nathanson's question and those flip-flopping sumsets?
Well, that's where proposition 2.4 comes in. It gives us the tools to make those sumset sizes dance to our tune. So proposition 2.4, this is where Kravitz shows us how to actually choose the right scales and with parameters to make those sumset sizes flip-flop, just like Nathanson was asking about.
Okay, walk me through this. How does he pull that off?
Remember that quantity ERK from the paper? It's kind of like a measure of how spread out the scales are within each group.
Right. So bigger ERK, more spread out the scales are.
Exactly. And what Kravitz does in proposition 2.4 is he shows us how to construct these specific sequences of scales, II and width parameter score, so that the relative sizes of these ERK values actually change depending on which H you're looking at.
Wait, so you're saying he found a way to make ERK bigger for some values of H and smaller for others just by tweaking the scales and the width parameter?
Yep, that's the gist of it. And this is crucial because remember, from lemma 2.3, we know that the size of the sumset is directly linked to the value of ERK. Ah, okay, so it's all coming together now. So by cleverly choosing the scales and the width parameter, Kravitz can actually control the relative sizes of the sumsets for different values of H. This is pretty mind-blowing stuff.
It is, isn't it? It's like he's found a way to encode the flip-flopping behavior directly into the structure of the sets themselves.
Okay, I'm following you so far. So, proposition 2.4 gives us the recipe for picking the right scales and width parameters to get this flip-flopping effect. But how does he actually use that to construct the sets themselves?
That's where theorem 1.1 comes in. This is where he puts all the pieces together and shows that this flip-flopping behavior isn't just a theoretical possibility, it actually happens.
Okay, let's dive into theorem 1.1 then. How does he actually build these flip-flopping sets?
So he starts by choosing specific values for those parameters we talked about, D, I, and gar, just like they were defined in proposition 2.4. You'll also see this large natural number m pop up in the proof. It's not super important what the exact value is as long as it's large enough. Okay, so we've got these carefully chosen parameters. What does he do with them?
He uses them to construct a set, AC, for each value of k from 1 to n, and each of these sets, AC, is built as a union of dilated arithmetic progressions, just like in lemma 2.3.
So it's like we have multiple versions of that special set A from before, each one tailored to a specific value of k.
Exactly. And the way these sets are constructed is, well, it's pretty ingenious. Each arithmetic progression within AC is scaled by muck, I, and it contains m elements, the integers from 0 to m1.
Wow. Okay, so we're taking these scales AC, stretching them out by a factor of m, and using them to build these sets AC. It feels like a very delicate balancing act.
It is, and here's where things get even more interesting. Remember HR, which was defined as more? Well, lemma 2.3 tells us that the size of the HR-fold sumset of AC, written as the absolute value of HR AC, is approximately proportional to m raised to the power of ERK.
Hold on, there's the ERK again. So the size of the sumset is linked to how spread out the scales are within each group, just like we were talking about earlier.
That's right. And this is where the clever choice of UK, I, and R, guided by proposition 2.4, really comes into play. Proposition 2.4 showed us how to pick these parameters so that the relative order of ERK changes for different values of R.
So it's all connected. We use proposition 2.4 to create these special sequences of scales and width parameters, and that leads to different values for ERK, which then controls the sizes of the sumsets. It's like a chain reaction of mathematical insights.
Exactly. And that's precisely how Kravitz demonstrates that you can actually have sets, in this case these AC sets, where their sumset sizes flip-flop as you change the number of times you're adding them to themselves.
Okay, so we've walked through the proof, we've seen all the moving parts, but I'm still curious, how does this proof change when we're talking about restricted sumsets?
That's the remarkable part. The proof works almost the same way, even for restricted sumsets.
Really? He didn't have to make any major changes to handle that extra restriction?
No, not really. The way he constructs the sets, the logic behind choosing the scales and the width parameter, it all stays pretty much the same.
That's pretty amazing. It really speaks to the elegance and the power of this approach. It's like he's uncovered this fundamental truth about how the size of sumsets can be controlled, whether they're restricted or not.
I completely agree. It's a beautiful example of how a carefully constructed proof can reveal deep connections and surprising results.
This has been an incredible journey so far. We've gone from a simple question about sumsets to this intricate construction that exhibits this crazy flip-flopping behavior.
I know, right? It's amazing how much depth there is to this problem, and we've only just scratched the surface.
Yeah, I was just thinking that. We've seen how Kravitz answered Nathanson's question, but now I'm even more curious about the bigger picture. Like, what are the implications of this result? Where does this research lead us next?
Those are fantastic questions. And I think they're the perfect segue into the final part of our deep dive, where we can step back and look at the broader context and explore some potential avenues for future research.
Okay, so we've really got into the nitty-gritty of Kravitz's paper, all the clever constructions and the logic behind it. But I'm wondering now, like, what's the big picture here? Why should we even care about these flip-flopping sumsets?
Yeah, that's a good question. It might seem like a pretty specific, even niche area of math, but I think Kravitz's work is pointing to something much deeper. It really challenges our intuition about, how much information we need to actually understand these mathematical objects. You might think, okay, if I know the size of a sumset for certain values of eighth, that'll give me some clues about what happens for other values.
I mean, it should follow some kind of pattern. Right?
Exactly. But Kravitz shows us that, nope, that's not always the case. These sumsets can be much more unpredictable than we might think.
So it's not just about the specific result itself, it's about this bigger message, about how we approach math, right?
I think so, yeah. It's a reminder that we should always be questioning our assumptions and being on the lookout for unexpected behavior, even in areas of math that seem pretty straightforward.
I like that. Like, don't get complacent, even when things seem simple. There might be a whole world of complexity lurking beneath the surface.
Exactly. And I think this idea goes way beyond just sumsets. It applies to all sorts of mathematical objects and problems.
So Kravitz really opened up a can of worms here, but in a good way. It makes you wonder, where do we go from here? What are some of the next steps in this line of research?
Well, for one thing, Kravitz focused on sets of integers in his paper. But what if we start looking at sets from other algebraic structures? Could we see the same kind of flip-flopping behavior with, say, matrices or polynomials?
Ooh, that's a really cool question. Like, is this phenomenon specific to integers, or is it something more universal?
Right. And there are other directions to explore, too. Like Kravitz's construction, it's pretty intricate, right? Could we find a simpler way to construct sets that exhibit this flip-flopping behavior?
I see what you mean. A simpler construction might give us a more intuitive understanding of what's really driving this phenomenon.
Yeah, and another question that comes to mind is, can we quantify this flip-flopping behavior more precisely? Like, can we say how many times the relative sizes of the sumsets can flip as each increases?
That's a great point. It feels like there's still so much more to uncover, Kravitz has given us this amazing glimpse into this unexpected behavior, but there are tons of questions left to answer.
For sure. And I think those questions are going to lead to some really exciting new research in the years to come.
This deep dive has really opened my eyes. It's amazing how a question that seems so simple, like just adding sets together, can lead to such profound mathematical insights and so many new avenues for exploration.
I couldn't agree more. It's a testament to the power of curiosity and the beauty of mathematics.
Absolutely. And a huge thanks to you, dear listener, for sending in this fascinating paper. It sparked a fantastic conversation, and I hope it's inspired you to keep exploring the endlessly fascinating world of mathematics. Until next time. Hey everyone, ready for another deep dive? Today we're tackling iterated sumsets.
Ooh, yeah.
It's fun.
Yeah, they're really cool. And we're looking at a paper called Relative Sizes of Iterated Sumsets by Noah Kravitz.
Cool.
And this is one of those papers that really makes you go, aha.
The good one.
When you start to really dig in and see how these things can change in ways you really wouldn't expect.
Yeah.
So
some surprising stuff.
Yeah, some surprising stuff. So let's start with the basics. What exactly is an iterated sumset?
Sure. So you start with a set like maybe we'll call it A.
Okay.
And you take all the possible sums of H elements from A. So you write that as HA, and more formally, it would be HA equals the set of all A1 plus and so on, up to where each of those A are elements of the set A.
Okay, so like if A was the set 1, 2, 3,
Okay.
and H was 2, then 2A would be all the sums you get by adding 2 numbers from A, right?
Right. So you'd have 2, 3, 4, 5, and 6. Exactly. Okay. Now the question is, how do the sizes of these sumsets compare as we change that H value, especially if we're looking at multiple sets?
That's where things get interesting. You might think that if one set starts off bigger, its sumsets will always be bigger. But that's not always the case.
Yeah, and that's what this paper is all about, right? It shows that those size relationships can flip-flop as H changes.
Exactly. In fact, Melvyn Nathanson asked, Can you have sets, let's call them A and B, where like A sumset is smaller than B's initially, then B's twofold sumset becomes smaller than A's, and then it flipped again for the threefold sumsets.
Whoa, hold on. So they're not just like steadily growing, one always bigger than the other. They're like leapfrogging each other.
Exactly.
That's kind of wild.
It is, and Kravitz didn't just say, yeah, that can happen. He proved a much broader theorem that works for any number of sets and any number of H values.
Okay, now I'm really intrigued. So let's dive into this theorem 1.1. What does it actually say?
It says that you can basically arrange the sizes of these H-fold sumsets in any order you want. Like for any number of sets, let's say n sets, any number of H values, you can make their sumset sizes go up and down in any sequence you choose. More formally, for each positive integer n, there exists a sequence Sn, which is 1, 2, and so on, of permutations of the set 1 through n, such that for every choice of positive integers r and h1 up to hr, there are finite non-empty subsets a1 up to bak, and of the integers for which the size of hk times a, say, is less than the size of hk times ask, for every k from 1 up to r minus 1.
Okay, I think I'm following. So like if I had three sets, A, B, and C,
Right.
I could make it so that for H equals 1, maybe A is the smallest, then B, then C. But for H equals 2, I could flip it around, so C is smallest, then A, then B. And then for H equals 3, I could mix it up again, and so on.
Exactly. You have total control over how those sizes compare as you change H.
That's amazing. It seems like you could create all sorts of crazy patterns with these sumsets. But how do you even begin to prove something like that? Where does Kravitz even start?
The key is using something called arithmetic progressions. These are sequences where the difference between each number is constant.
Like 2, 5, 8, 11.
Yeah, exactly like that.
Okay, so basic sequences. But how do those help with sumsets?
Well, when you start forming sumsets from arithmetic progressions, the sizes grow in a very predictable way. And that's what Kravitz uses to create these sets that have that flip-flopping behavior. It's all about how you scale and shift those progressions.
So he's using these simple building blocks to create something much more complex.
Exactly.
Okay, that's pretty clever. But I'm guessing it's not just a matter of throwing some arithmetic progressions together, right?
Right. There's a lot more to it. Kravitz develops 3 key lemmas, which are like mini theorems that he uses to build up to the proof of the main theorem.
So it's like a step-by-step process, each lemma getting us closer to the final result.
Exactly. Think of them as tools that he uses to analyze and manipulate those sumsets.
Okay, I'm starting to get the picture. So let's start with the first lemma, lemma 2.1. What's its role in all of this?
Lemma 2.1 is all about estimating the size of a sumset when you're dealing with the union of several sets. So imagine you have sets A1, A2, and A3, and you want to know how big their combined sumset is. That's HA1 plus HA2 plus HA3.
Okay, so it's like taking all those sets, mixing them together, and then figuring out how many different sums you can get.
Exactly.
And this lemma gives you a way to estimate that.
It gives you an upper and a lower bound for the size of that combined sumset. Part 1 tells you that the size of that sumset can't be bigger than the product of the sizes of the individual sumsets, which kind of makes sense.
Yeah, like you're limited by how big those individual pieces are.
Right. And then part 2 gives you a lower bound by finding a smaller set that's guaranteed to be inside the combined sumset.
Oh, I see. So you're kind of sandwiching the size between two limits.
Exactly. And to do that, you have to look at the structure of those sets. Like if each AI is a union of shifted and scaled copies of other sets, that's where the arithmetic progressions start to come in, then you can find specific elements from each of those copies and add them up to get a set of sums that's definitely a subset of the combined sumset.
Okay, so it's like strategically picking ingredients from each set to create a smaller dish that gives you a minimum size for the whole meal.
A good analogy.
So that's lemma 2.1. It gives us a way to bound the size of these combined sumsets.
Yes, and that control over the size is really important for proving the main theorem because it lets us manipulate those sizes and make them flip-flop like we want.
I see. So lemma 2.1 sets the stage for this whole size manipulation game.
Exactly. It's one of the key tools that makes everything work.
All right, I'm ready for the next tool. What's special about lemma 2.2?
Lemma 2.2 introduces this idea of additive independence.
Additive independence. It sounds kind of complicated.
It's actually pretty intuitive. Think about it. When you add elements from two sets together, sometimes you can get the same sum in multiple ways.
Right, like if one set has 1 and 2 and the other has 3 and 4, you can get 5 by adding 1 and 4, or 2 and 3.
Exactly. But if your sets have this special property, you can make sure that every sum you create is unique, like a fingerprint.
So it's like there's only one recipe to get to that particular sum.
You got it. And Lemma 2.2 gives you a condition to check if two sets have this property. It says that if the difference between any two elements in one set is always different from the difference between any two elements in the other set.
So like the gaps between the numbers are all unique.
Yeah, something like that.
Okay.
Then those sets are additively independent.
I see. So it's about how those sets are structured internally.
Right.
And why is this so important for Kravitz's proof?
Because when you have these additively independent sets, calculating the size of their combined sumset becomes much easier. It's just the product of their individual sizes. And that makes it easier to compare those sizes and see how they change as you increase h.
Ah, so this additive independence simplifies things and lets him really focus on that flip-flopping behavior.
Exactly.
Okay, 2 lemmas down, 1 to go. What does lemma 2.3 bring to the table?
Lemma 2.3 is where we really start to see those arithmetic progressions in action. It gives you a precise estimate for the size of a sumset when the sets are constructed in a specific way, using scaled versions of arithmetic progressions.
Okay, so we're back to those sequences with the constant differences.
Yeah.
But what does scaled mean in this context?
It means you're basically stretching or compressing those progressions by multiplying each term by some factor.
Oh, I see. So it's like taking those evenly spaced markings on a ruler and making them closer together or further apart.
That's a great way to visualize it. And Lemma 2.3 tells you how to calculate the size of the sumset based on those scaling factors and a few other parameters. There's a parameter gamma that controls how those progressions are grouped together, and then a parameter m that kind of stretches everything out even more.
So it's like a recipe for building these sumsets with very specific properties.
Yeah, that's a good way to put it. And that precise control over the size is what allows Kravitz to create that flip-flopping behavior. He can fine-tune those parameters to make those sizes change in exactly the way he wants.
Okay, this is starting to feel like a very intricate machine with all these moving parts working together.
It definitely is.
We have those arithmetic progressions, the scaling factors, the grouping parameters. It's a lot to keep track of.
But it all comes together beautifully in the end.
I'm eager to see how. But for now, I think our listener might need a little time to digest all of this.
Yeah.
We've covered a lot of ground already. We'll pick up this mathematical adventure in the next part, where we'll see how Kravitz uses these tools to prove Theorem 1.1 and delve into what it all means for our understanding of set growth. Stay tuned.
Yeah, stay tuned. It's going to be a fun ride.
All right, welcome back to our deep dive into iterated sumsets. We've explored those clever lemmas, and now it's time for the main event. I'm excited to see how Kravitz uses these tools to actually prove this wild Theorem 1.1. The idea that you can arrange sumset sizes in any order you want still feels kind of mind-boggling.
Yeah, it definitely challenges our intuition about how sets grow. But that's what makes this paper so cool. It shows how rigorous math can lead to surprising results.
Absolutely. So let's walk through this proof. We know lemma 2.3 is key. That's the one about those scaled arithmetic progressions.
That's the one.
Okay. So how does he actually use it to make these sumset sizes flip-flop like that?
Well, remember, the key is to choose those parameters carefully. The scaling factors, that gamma thing for grouping, and m, the stretching factor, it's all about getting them to work together to create those flips.
So it's like a balancing act.
Yeah, exactly. Like you're trying to choreograph a dance where the dancers are the sizes of these sumsets, and you got to make sure they move in the right order at the right time.
I like that analogy.
So to see how it works, let's imagine a simple version of the proof with just two sets, A and B, and we want their sumset sizes to flip just once.
Okay.
Like, say for h equals 1, we want A to be smaller than B.
Okay.
But for h equals 2, we want B's twofold sumset to be smaller than A's.
Gotcha. So a single flip.
Right. So first, we've got to build these sets A and B using scaled arithmetic progressions.
Right. So where do we start?
Let's start with set A. We'll build it using two scaled arithmetic progressions. The first one's super simple, 0, m, 2m, and so on, all the way up to m-1 times m, where m is that stretching factor.
Okay, so it's like a ruler with marks every m units.
Yeah, exactly like that.
Okay.
And then the second arithmetic progression we'll use for A is scaled by a factor of, let's say, 10m. So it'll be 0, 10m squared, 20m squared, up to m-1 times 10m squared. So the spacing between the marks on this ruler is way bigger, 10m squared, compared to m on that first ruler.
Right, so the second one's kind of zoomed out.
Exactly.
Because markings are much further apart.
Yeah. And set A is just the combination of those two rulers, all those markings put together. So it's got a bunch of really close marks from the first ruler and then those spaced out marks from the second one.
Got it. Now what about set B?
We'll do something similar for B, but with a little twist. We'll use two scaled arithmetic progressions again, but this time the first one will be scaled by 5m, so 0, 5m squared, 10m squared, and so on. And the second one by 15m, so 0, 15m squared, 30m squared, and so on.
Okay, so both of B's progressions have marks that are further apart than A's first progression, but closer together than A's second progression. It's like they're in between.
Exactly, they're right in between.
Yeah.
Now, when you calculate the sumsets for h equals 1,
Right.
something interesting happens. B actually ends up having a larger sumset than A.
Really? Why is that?
It's because of those scaling factors. 5m and 15m we chose for B.
Okay.
Because B's marks are more spread out, its sumset ends up being bigger for h equals 1.
So for h equals 1, it's like B covers more ground because it's more spread out.
Precisely. But here's the cool part. When we go to h equals 2, things change completely.
Uh-oh.
Now we're adding any two marks together, and that's where those really close together marks in set A from that first ruler really make a difference.
I see. So those close marks in set A start creating a lot more combinations.
Right. Way more than B can make with its more spread out marks.
It's like they give set A a hidden advantage.
Exactly. So even though B had a bigger sumset at first, A catches up and overtakes it when h equals 2 because it can create so many more unique sums with those close together marks.
Wow, that's sneaky.
So that's how you get that flip-flop. And this is just a simplified example, but it shows how Kravitz uses the scaled arithmetic progressions and that lemma 2.3 to create this surprising behavior.
Okay, that's really neat. But I know the actual proof of theorem 1.1 is way more complicated than this two-set example.
Yeah.
How does he handle the general case with all those sets and h values?
Well, it definitely gets more involved, but the basic idea is the same. You carefully construct these sets using scaled arithmetic progressions.
Okay.
But to manage all that complexity, Kravitz introduces some new notation. He uses I to represent the scaling factor for, let's say, the I arithmetic progression in the kth I set.
So each set has a whole sequence of scaling factors that control how stretched or compressed those arithmetic progressions are.
Exactly. It's like having a bunch of rulers with different spacings between the marks.
Got it. But how does he make sure that the sumset sizes end up in the right order for all those different h values?
That's where those grouping values come in. Remember?
Yeah, those grouping parameters. What are they grouping exactly?
Yeah. They're grouping those scaling factors, the I, into clusters.
Clusters. What do you mean by that?
Think back to lemma 2.3.
Okay.
That one dealt with sets that were built from unions of scaled arithmetic progressions, right?
Right.
Those Gnig values tell you which of those scaled progressions should be considered close to each other. Like they control which marks on your rulers are kind of bunched together.
Oh, I see. So it's about how those scaling factors are arranged relative to each other.
Exactly. And this grouping is really important for getting those sumset size estimates just right. And to make sure everything lines up perfectly, Kravitz uses proposition 2.4.
Proposition 2.4. What's that all about?
That's where he establishes a very specific relationship between those scaling factors and those grouping parameters.
So it's like the rule book that makes sure all those parts work together.
You got it. Proposition 2.4 makes sure that for every h value, those sumset size estimates, which depend on those scaling factors and grouping parameters, fall into the right order.
I see. So it's like a whole system of checks and balances.
Yeah, pretty much.
To guarantee those flips happen exactly when they're supposed to.
Right.
Okay, that makes sense. But I imagine those rules, or like the math behind them, must be pretty complicated.
They are.
Can you give us an example?
Yeah, one of the key inequalities in Proposition 2.4 says that for every r from 1 up to n minus 1, you need to make sure that her plus 1 minus 1 times r is less than hr minus 1 times r plus 1d.
Whoa, okay, that's a lot of symbols.
It is.
Can you break that down a bit?
Sure, so the inequality is all about making sure the sumsets are arranged in the right order for two consecutive h values, like hr and r plus 1.
Okay.
And it's comparing those scaling factors, the ahs, for the sets that should be smaller and bigger at those h values.
So it's like making sure the smaller set's contribution to the sumset stays smaller, even as age changes.
Exactly. It's a way to enforce that flip-flop.
That's really clever. I'm starting to see just how much planning goes into creating those flips. It's like every detail matters.
It really does. And that's just one piece of the puzzle. The whole proof is a symphony of inequalities like that, all working together to make those sumset sizes dance just the right way.
It's amazing how much complexity can arise from something as seemingly simple as adding sets together.
Yeah, it is.
And we're back for the grand finale of our deep dive into iterated sumsets. I have to say, this journey has been full of surprises. It's like Kravitz is a mathematical magician, pulling off these incredible feats with sets and their sums.
He really is. The level of ingenuity in this proof is just remarkable. We've seen how he uses those scaled arithmetic progressions as building blocks, carefully chooses those parameters, and then ties everything together with proposition 2.4, ensuring that all of those sumset sizes line up just right.
Yeah, it's like he's constructed this intricate clockwork mechanism where every gear is perfectly calibrated to create this specific outcome.
But I'm still a bit hazy on the details of proposition 2.4. Those inequalities you mentioned, the ones that relate those parameters, they seem to be the key to orchestrating those flips, right? Absolutely. They lay down the law, so to speak, dictating how those scaling factors and grouping parameters need to behave to create the desired flip-flopping pattern. To get a clearer picture, let's look at one of those key inequalities again. Remember that one we talked about? For every r from 1 up to n-1, we need to have her plus 1 minus 1 times s and hr minus 1 times r plus 1 d.
Yeah, no, that one definitely caught my attention. It seemed to be comparing those scaling factors of adjacent sets in a way that depended on the h values. But I'm still not quite grasping what it's really telling us.
Well, let's break it down. This inequality is all about making sure those sumset sizes are arranged correctly for two consecutive h values, hr and her plus 1. It's like a local check to ensure things are moving in the right direction as we step from one h to the next. On the left side, we have her plus 1 minus 1 multiplied by os or r. Remember that a term represents the scaling factor for, let's say, the d arithmetic progression in the set. And desar is that permutation that tells us how we want the sets ordered for a particular h. So that os is basically controlling the spacing on the metaphorical ruler for the set that should be smaller at that h value.
Okay, so the left side incorporates the scaling of one set and multiplies it by something related to the bigger h value, her plus 1. What about the right side?
The right side is similar. It's got hr minus 1 times os plus 1, which is the scaling factor for that same d-dth arithmetic progression, but in the set that's supposed to be larger at that h.
Ah, I see. So it's comparing the scaled contributions of those two sets, taking those specific h values into account. By keeping that inequality true, Kravitz guarantees that the set that should be smaller is contributing less to the total sumset size, even as h changes.
Precisely. It's a subtle but powerful way to enforce that flip-flopping, and that's just one of the many inequalities laid out in Proposition 2.4. The full proposition is a system of these carefully crafted relationships, ensuring that all those scaling factors and grouping parameters cooperate to produce exactly what we want.
It's amazing how much precision and thought goes into creating this seemingly simple behavior. It really shows how powerful mathematical reasoning can be in uncovering these hidden truths.
It really does, and I think that's a key takeaway from Theorem 1.1. It challenges our intuition about how sets grow. We often think that if a set starts off bigger, it'll always stay ahead. But Kravitz shows us that's not always the case. Those size relationships can shift and change in surprising ways as we move through those h values. It's a fascinating interplay of growth and structure.
It reminds us that even in areas of math we think we understand well, there can be these unexpected twists and turns.
Exactly. And as we wrap up this deep dive, I want to leave our listener with a final thought. Kravitz focused on sets built from arithmetic progressions. But what happens if we go beyond that? What if we explore different kinds of sets? Sets with more intricate structures? Could we discover even more exotic patterns in how those sumsets grow?
That's a great question to ponder. It seems like we've only just begun to explore this fascinating corner of the mathematical universe. There's so much more to uncover.
Absolutely. So to our listeners, keep those mathematical minds active. Keep asking questions. Keep exploring. Who knows what amazing discoveries await?
Couldn't have said it better myself. Thanks for joining us on this deep dive into the world of iterated sumsets. It's been an amazing journey. All right, get ready for a deep dive, folks. We're taking a plunge into the fascinating world of iterated sumsets.
We're going to be exploring an intriguing question posed by mathematician Melvyn Nathanson. Can the relative sizes of sumsets actually flip-flop as we delve deeper, adding more and more elements?
We're talking about Noah Kravitz's paper, where he tackles this head-on.
And what's fascinating, he actually found a way to construct sets that exhibit exactly this kind of flip-flopping behavior.
So before we get ahead of ourselves, let's start with the basics. You mentioned sumsets. Could you remind us what those are again?
Absolutely. Imagine a set of numbers, we'll call it A. The sumset, denoted as H, where H is a natural number, It's basically the set you get by adding H elements from A together.
Oh, and we can repeat elements, right?
That's right. You can use the same number multiple times.
So like if set A is 1, 2, then 2A would be 2, 3, 4. Because we get 2 from 1 plus 1, 3 from 1 plus 2, and 4 from 2 plus 2.
You got it. That's exactly it. Now, things get really interesting when we start talking about iterated sumsets.
Which is where we increase the value of H. Right, we're essentially adding more and more elements together.
Precisely. And as you might imagine, as H increases, the sumsets can grow in unexpected ways. Those size relationships might not always behave as we'd initially predict.
And that leads us to Nathanson's question, right?
Yeah.
Is it possible to have two sets, let's say A and B, where the size of 2A is smaller than the size of 2B, but then when we jump to 3A and 3B, that relationship flips, with 3B becoming smaller?
That's the crux of it. It's like those sumsets are playing a game of leapfrog. And Kravitz found a way to construct sets that actually do this.
That's pretty mind-blowing. He uses these homogeneous arithmetic progressions at different scales to do this, right?
That's right. Sounds a bit complicated, but we'll break it down.
Definitely. All right, so let's back up a bit and get a clear picture of Nathanson's question. What's the precise mathematical language he used?
Sure. So Nathanson's question asks whether there exist finite sets, A and B, subsets of the integers, and natural numbers h1, h2, and h3, where h1 is less than h2, which is less than h3, such that the cardinality of h1a is less than the cardinality of h1b. The cardinality of h2b is less than the cardinality of h2a.
Okay, so we're taking these three snapshots of the sumsets for each set.
And we're looking to see if those size relationships can reverse as we move from h1 to h3. And lastly, the cardinality of h3a is greater than the cardinality of h3b.
I see. So it's all about how the properties of sets, specifically their additive properties, change when we repeatedly add elements together.
Exactly. Can we predict what happens at higher h values based on what we observe at lower ones? Nathanson's question suggests it might not be so straightforward.
So there's an element of unpredictability. It's not a simple linear progression.
Exactly. And that's what makes Kravitz's work so intriguing. He goes beyond a simple yes or no answer.
He actually provides a way to construct sets that exhibit this flip-flopping behavior, right?
You got it. And his approach is quite elegant, even though it might seem complex at first glance.
Okay, I'm definitely intrigued. Now, Kravitz's main theorem, it's not just about two sets and three h values, is it?
No, it's much more general than that. In Theorem 1.1, he shows that for any number of sets, which we'll call n, and any number of h values, denoted r, we can construct sets such that the size relationships between their sumsets can actually follow any order we want.
It's like he's giving us a recipe to create sets with very specific sumset behavior.
Exactly. And to represent those desired size orderings, he uses permutations.
Denoted by the Greek letter sun, if I remember correctly.
You're right. So for each h value, you have a permutation that tells you which sumset should be bigger, which should be smaller, and so on.
Okay, that makes sense. So Theorem 1.1 is like a master key. It unlocks all these different possibilities for how we can construct sets and control their sumset behaviors. And Nathanson's question is just one special case, one specific example within this broader framework.
Precisely. You could say Nathanson's question was the spark that ignited Kravitz's exploration, ultimately leading to this more general result.
Now, how does Kravitz actually build these sets? What's the step-by-step process, or at least the key building blocks?
He relies on several lemmas, each of them a crucial tool for analyzing sumset sizes. These lemmas lay the foundation for his proof.
Okay, let's take a closer look at these lemmas then. Where do we start?
We start with lemma 2.1, which focuses on the sumset of a union of sets. Think of a set A that's actually made up of several smaller sets.
Like breaking a complex structure into smaller, more manageable pieces.
Exactly. So lemma 2.1 basically tells us how the size of the sumset A is related to the sizes of the sumsets of those smaller sets.
So it gives us a way to control the size of the larger sumset based on how it's built from these smaller parts.
Precisely. And there's this concept of the identity element, often represented as 0, which plays a role here, but it's more of a notational detail than a central concept.
Got it. Okay, what's next? What's the next piece of this puzzle?
We then move on to lemma 2.2, which introduces this very important idea of additive independence.
Additive independence. What is that exactly?
Essentially, if you have two sets, A and B, and the only way to get the same sum from both is by adding the identity element to itself, then the size of the sumset A plus B is simply the product of the sizes of A and B.
Okay, so it's about these sets having distinct ways of generating sums.
Right. And why this additive independence is so important in Kravitz's proof is because he wants to build sets where he has very precise control over the sizes of those sumsets.
It's all about taming the potential complexity that arises when you're dealing with these iterated sumsets.
Exactly. That brings us to lemma 2.3, probably the most critical lemma in the entire proof.
Is this where we finally encountered those homogeneous arithmetic progressions at different scales?
You got it. Things start to get really interesting here.
I'm all ears. Let's dive into those intriguing structures. Can you explain what those are and how they're used to build these special sets?
Let's start with a homogeneous arithmetic progression. Just a sequence of numbers where the difference between any two consecutive terms is constant.
Like 2, 4, 6, 8. A common difference of 2.
Exactly. But now, imagine taking a basic arithmetic progression and stretching or compressing it by multiplying each term by a certain factor. That's where the different scales come in.
Oh, I see. Like, you could have one progression with 1, 2, 3, 4, and another with 5, 10, 15, 20. The second one's just the first one scaled up by a factor of 5.
That's it. And Kravitz constructs the set A by taking the union of several of these scaled arithmetic progressions.
Using a set of non-negative integers to determine those scales, right?
Exactly. Those are denoted by A, avoir 1, up to I'd. These I values dictate how much each progression is stretched or compressed.
So if I1 is 2 and I2 is 5, we have one progression scaled by 2, another by 5, and they both become part of set A.
Precisely. But there's one more layer to this. Kravitz uses a parameter go to determine how these I values are grouped.
Ah, so it's not just about the individual I values, but how they're clustered together.
Exactly. The idea is to create clumps of I values that are close together, with bigger gaps separating those clumps.
Clumps based on okay, but can you give me more concrete examples?
Sure. Let's say our I values are 0, 1, 7, 9, 10, 20, 30, and 32. If we set I to be 3, we can group these based on their proximity.
So 0, 1 form one clump.
Right? Then 7, 9, and 10 form another clump since they're all within 3 of each other.
20 would be on its own then.
Yes, and finally 30 and 32 form the last clump. These clumps are formally called equivalence classes, and each one has a smallest I value, denoted Schneemann, and a largest Cmax.
And these Kleeman and Cmax values are important for the estimate in lemma 2.3, right?
Right. That's where things get really interesting. Lemma 2.3 gives us both upper and lower bounds for the size of A, and those bounds are expressed in terms of those Tmin and Cmax values for each clump.
And how does this relate to the parameter m that Kravitz uses?
Well, the lemma essentially says that for large values of m, the size of A is roughly proportional to the product of m raised to the power of Cmax Cmin plus 1 board for each of those clumps.
Whoa, okay. That exponent seems pretty dense. Can you break that down a bit? What's the meaning of Cmax Cmin plus Keen plus 1?
Think of it this way. Cmax Cmin tells us the range or the width of each clump, how spread out those I values are within that clump.
And APA controls how close those values need to be to belong to the same clump, right?
Right. So the bigger this entire exponent is, the wider the range of S values within that clump, which counterintuitively can lead to a larger sumset.
That's interesting. So it's not just about the individual off values themselves, but also about how they interact and are grouped based on egg.
Exactly. That's the crucial insight lemma 2.3 gives us.
So we've got these off values determining the scaling of our arithmetic progressions. They're grouped into these clumps based on A. And lemma 2.3 connects the structure of those clumps to the overall size of the sumset. What's next in this proof? How do we actually get to that final theorem, the one that tells us we can create those flip-flopping sumsets?
Well, proving the upper and lower bounds from lemma 2.3 involves some pretty technical stuff. We use techniques like inclusion-exclusion, a way of counting elements without overcounting, and we apply lemma 2.2 iteratively, utilizing that additive independence principle to simplify the calculations of sumset sizes.
Okay, so those techniques are crucial for making sure the estimate in lemma 2.3 holds up. And then comes proposition 2.4, right?
Exactly. This proposition demonstrates that we can choose those ONS values in a very specific way so that we get the flip-flopping behavior we're looking for.
So we have all the ingredients, the odd values, those lemmas, and proposition 2.4 shows us how to mix them together in just the right way to get those flip-flopping sumsets.
Exactly. And then the proof of theorem 1.1 is just about putting all the pieces together.
We take the sets constructed based on proposition 2.4, plug them into lemma 2.3, and voila! We've got sumset sizes that satisfy the conditions of the theorem.
Exactly. And it's all made possible by those meticulously chosen parameters.
This is incredible. It's like watching a master chef at work. It's clear we've just scratched the surface here.
We've laid the groundwork, understanding the heart of Kravitz's proof.
We've explored sumsets, those key lemmas, and gotten a glimpse of how he uses them to construct those sets with those incredible properties.
Indeed, a solid foundation.
In part 2, we'll pick up where we left off and dig deeper into proposition 2.4. We'll uncover the techniques Kravitz uses to choose those eigenvalues and see those flip-flopping sumsets come to life.
Sounds good. I'm looking forward to it. Welcome back. Last time, we laid out the groundwork, the core concepts and the key lemmas that lead to Kravitz's amazing construction.
Yeah, we explored those homogeneous arithmetic progressions at different scales, those clumps of values based on, and of course, lemma 2.3, which connects those clumps to the sumset size.
Exactly. Now it's time to roll up our sleeves and dive into proposition 2.4, where Kravitz shows how to carefully select those eigenvalues.
To create sets that actually show that flip-flopping behavior with their sumset sizes, right?
That's right. It's like a delicate balancing act.
Okay, I'm ready to see how he does it. What's the first step?
Well, first, we got to set the stage by defining those WAP values. Remember, Kravitz controls how close those Asha values need to be to get grouped together into clumps.
Right, yeah.
So Kravitz sets each WAR, where your goes from 1 to R, that's the number of H values we're considering. He sets each of those GARTs to be a massive number, specifically 10n raised to the power of 10.
Wow, those are some huge numbers. Why so big? I would have thought smaller Barch values would mean tighter clumps and lead to bigger sumsets.
You'd think so, right? But actually, those huge values ensure that the clumps of Va values are really well separated. And remember what lemma 2.3 told us. The sumset size is related to the width of those clumps.
Ah, I see. By making I super big, he's basically stretching out those clumps, giving a wider range of values within each clump.
Exactly. And that wider range, even though it seems counterintuitive, is what lets him fine-tune those sumset sizes to get that flip-flopping behavior.
Okay, so bigger values, got it. Now, how do we pick those values to actually build the sets that'll behave the way we want?
This is where something called generalized arithmetic progressions come in. For each set, Kravitz constructs a sequence of values using this special kind of progression, one where those side lengths increase really fast.
Hold on, let's back up a sec. I know what a regular arithmetic progression is, but what's a generalized one?
Think of a normal arithmetic progression as a staircase, right? Evenly spaced steps. A generalized one is like a staircase where the steps can have different sizes. You're not adding a constant difference each time.
So it's like a more flexible staircase. You can adjust the steps.
That's it. And Kravitz makes those step sizes, those side lengths, increase super fast. This makes sure the values within each clump are close together, but the gaps between clumps stay really big because of those giant live values.
All right, I'm following so far. We've got those I values in a generalized arithmetic progression with fast-growing side lengths. And those I values get grouped into clumps based on those huge values. Can you give me an example to help visualize this?
Sure. Let's say we've got two sets, so n is 2, and we're looking at 3 h values, so r is 3.
Okay, so that means we've got 3 values 1 and the 3, which, based on Kravitz's formula, are going to be some seriously huge numbers.
Right. Now, for each set, let's say set 1, we create a sequence of values using that generalized arithmetic progression with those fast increasing side lengths. The exact formula for those values gets a bit complex, involving those giant I values and those permutations that tell us how we want the sumset sizes to be ordered.
So lots of calculations behind the scenes to get those values just right. But the main point is they're arranged in a way that makes those specific clumps, with those wide ranges of I values within each clump.
Precisely. Remember those ER values we talked about before?
They're calculated based on the common and CNAX of each clump, right? And they're important for the proof.
Yeah. They kind of resemble those exponents in lemma 2.3, the ones that link the sumset size to how those clumps are structured.
Right, right. I'm starting to see how this all connects.
So by choosing the right IR values, Kravitz makes sure those E values have a specific order. For each error value, which corresponds to an H value, those E values will be arranged according to the permutation jog.
So let me get this straight. If, for example, RE1 and the permutation 1 is 21, meaning we want the sumset for set 2 to be smaller than the sumset for set 1.
Then Kravitz makes sure the E value for set 2 is smaller than the one for set 1.
Exactly. And this happens for all the error values and their corresponding permutations.
You got it. By carefully setting up those sequences and those giant WA values, he makes those E values, and therefore the sumset sizes follow those predetermined permutations perfectly.
Wow, that's amazing. It's like he's programmed those sets to behave in a very specific way.
It really is, and it shows how powerful mathematical tools can be when it comes to manipulating these abstract objects.
All right, so we've set up our I values. What's next in this process?
Now we formally define the sets themselves using those carefully chosen I-values. Kravitz calls these sets ACK, where K goes from 1 to n, the number of sets we're working with. Remember, each ACK is created by combining those scaled homogeneous arithmetic progressions.
With the scaling determined by those R-values, right?
Exactly. To make sure these sets have the properties we want, Kravitz introduces another parameter, m. He makes sure m is a really big number.
So m is like a global scaling factor, making sure everything is big enough to work with those massive values and those carefully arranged values.
That's a great way to think about it. Now, with those sets ACK defined, we can finally connect everything and prove theorem 1.1.
Okay, let's see how all these pieces fit together. We've laid the groundwork, defined our sets, and now it's time for the grand finale.
Right. We go back to lemma 2.3, which, if you recall, gives us an estimate for the size of the sumset ACK, where art corresponds to the ACK value we're looking at.
Yeah, that estimate tells us how the sumset size relates to those Km and Cmax values, which are determined by our carefully chosen and ek values.
Exactly. And because we were so careful in constructing those ek values, we know the size of each sumset ACK will be connected to those e values. And remember, we made sure those e values are ordered according to those permutations we chose at the beginning.
So it's like those permutations are conducting the whole show, making sure the sumset sizes follow the exact order we want.
That's a perfect way to put it. And that's basically how Kravitz's proof works. By plugging those carefully constructed sets, locking into lemma 2.3, he shows that those sumset sizes do indeed obey those permutations, leading to that flip-flopping we've been exploring.
Incredible. It all comes together so beautifully.
It really does. And it highlights the elegance of mathematical reasoning and construction. Even though the proof might seem complex, the ideas behind it are actually quite elegant.
Well, we've definitely covered a lot in this part of our deep dive. We went through the details of Proposition 2.4, saw how Kravitz chooses those and got values, and finally connected everything to prove Theorem 1.1.
Indeed. We've witnessed the intricate interplay of construction, estimation, and permutation.
In the final part of our deep dive, we'll step back and look at the bigger picture. What does this result actually tell us about sets, about mathematical thinking, and what are the potential applications of this seemingly abstract discovery?
It's a journey from the specific to the general, from technical details to broader implications. I'm looking forward to exploring that with you.
Welcome back to our deep dive. We've been on quite a journey through the intricate world of iterated sumsets.
We've really dug deep into the details of Kravitz's proof, haven't we? Uncovering those remarkable sets that exhibit that flip-flopping behavior in their sumset sizes.
Yeah, it's been a wild ride. We've explored those homogeneous arithmetic progressions, those clumps of A values based on San, and seen how he so meticulously crafts those ANA values to get those sumsets to, follow those predetermined patterns.
Absolutely. It's quite a feat of mathematical construction.
It really is.
Yeah.
But now that we've gone through all the technical stuff, I'm thinking about the bigger picture. What does this all mean, in the grand scheme of things?
That's a great question. It is important to step back sometimes and think about the broader implications of a result like this. On one level, it really highlights the complexity and sometimes surprising behavior we can find, even in seemingly simple mathematical systems. I mean, the fact that those sumset size relationships can actually reverse.
Yeah. It's not always what we expect.
Right. And it's not something we can always predict just from looking at those lower H values. It really challenges some of our basic intuitions about how sets evolve under repeated addition.
It's like a reminder that there are still so many uncharted territories in mathematics. Even in areas that seem well explored, there are still surprises waiting to be discovered.
Absolutely. Kravitz's work really emphasizes that we can't always just rely on limited observations and make assumptions. Things aren't always as straightforward as they seem.
So it's a cautionary tale for mathematicians, like stay humble and expect the unexpected.
In a way, yes. But I think it's also incredibly exciting. It opens up all these new avenues for exploring sumsets. The techniques he uses and the insights from his proof, they could lead to all sorts of new discoveries.
So it's not just about answering Nathanson's original question, but about pushing the boundaries of what we know in this area of math.
Exactly. It's about possibilities and connections to other areas of math, maybe even beyond math.
And, Kravitz's work is just a beautiful example of abstract thinking and the elegance of mathematical structures.
Oh, definitely. That proof, even though it's complex, is really a work of art.
It reminds us that math is more than formulas and calculations, right? It's a way of thinking, a language for understanding the world in a deeper way.
Well said. And while the specifics of Kravitz's construction might seem, a bit esoteric, those fundamental principles of logic and creativity and the pursuit of knowledge,
The universal, right?
exactly, they go beyond any one field.
Well, I think this deep dive has been an amazing journey. We've unpacked this complex proof, wrestled with these fascinating concepts like those homogeneous arithmetic progressions, and come away with a deeper appreciation for the beauty of mathematical exploration.
It's been a pleasure exploring this with you and our listeners.
Now, before we wrap up, a final thought for our listeners. We've seen how Kravitz's work shows us some unexpected behavior with sumsets. But what other surprising properties might be out there? What other mysteries are waiting to be uncovered in this world of iterated sumsets?
That's a great question to leave our audience pondering. And for anyone who wants to dive deeper, I definitely recommend checking out the paper by Melvyn Nathanson that Kravitz references in his work. It gives a really good background on the growth of these iterated sumsets, and it explores some related questions that are still puzzling mathematicians today. It's a great place to start for anyone who wants to embark on their own mathematical adventure.
Absolutely. Great suggestion. Well, on that note, we've reached the end of our deep dive. Thanks for joining us on this exploration. Until next time, keep those mathematical minds curious and keep exploring. Welcome to another deep dive. Today, we're going to be tackling this really interesting paper all about iterated sumsets.
Ooh, sumsets.
Yeah, so this is on the relative sizes of iterated sumsets, and it's by Noah Kravitz.
Okay.
So have you ever heard of iterated sumsets?
I have, yeah. It's basically like how many unique sums you can get when you add the elements of a set to itself over and over again.
Right, exactly. And it turns out, you would think that if you have a set A,
Right.
and you add it to itself twice,
Okay.
and you get a certain number of sums,
Right.
and you have set B, and you add that to itself twice,
Yeah.
and you get fewer sums,
Right.
you would think that that would always be the case, right?
Yeah.
Like if you add it 3 times or 4 times, the set A is always going to have more sums than set B.
Yeah, that seems pretty intuitive.
Right, exactly. But that's not always the case, and that's what this paper is all about.
Oh, interesting. So it could flip-flop which one has more sums as you keep adding them to themselves.
Exactly, and that's exactly what Kravitz proves in this paper. He shows that this flip-flopping phenomenon, that's what he calls it.
Okay.
It's not just a quirk. It's actually a fundamental part of how sets in addition work together.
Wow. Okay. So even if A has more twofold sums than B, B could have more threefold sums. And then maybe A has more fourfold sums again.
Exactly. And it can get even more complicated than that. He generalizes it to any number of sets
Okay.
and any number of additions.
So we could have 5 sets and the order of which one has the most sums could change like crazy as we go from twofold sums to threefold sums to fourfold sums and so on.
Exactly. And the main result, he calls it theorem 1.1.
Okay.
It basically says you can arrange these sets so that their sumset sizes change order however you want.
That's wild. So knowing the sumset sizes for the first few additions tells us nothing about what happens as we keep going.
Yeah. Right. Yeah. There's no predictable pattern, which I think is super surprising.
Yeah.
It's more evidence that math is weirder than we think it is.
Totally. So how does he even begin to prove something like that? What kind of tools does he use?
Yeah. So I skimmed through the paper and I saw something about unions of homogeneous arithmetic progressions at different scales. And honestly, I was I don't know what that means.
Right. That sounds a bit intimidating. It's way beyond just adding numbers together, right?
Right.
But I guess you could think of it like building with Legos, maybe?
Legos?
Yeah, imagine each set is a collection of these Lego blocks, right? And the blocks are all made of numbers.
Okay.
But they're spaced out in a very specific way.
Okay.
And these blocks, they're arithmetic progressions. Have you heard of those?
Yeah, it's just a sequence where you keep adding the same number.
Exactly. So you've got 2, 4, 6, 8 or whatever. But Kravitz arranges these Lego blocks of numbers in a very strategic way. And it's all about controlling how the sum sets grow.
Okay, so he's an architect, but with numbers.
Yeah, exactly. He's designing these sets with deliberate gaps between the numbers to create these weird flip-flop patterns in the sum set sizes.
I'm starting to see the picture. So how does he actually analyze what happens to the sum sets when he adds these carefully constructed sets together multiple times?
Well, a big part of it involves bounding the sumset sizes, like finding a mathematical ceiling and floor for how big or small they can be.
Okay, that makes sense. So
Yeah.
how does he figure out the upper bound, like the biggest the sumset can possibly be?
He uses something called an inclusion argument. It's basically showing that the sumset must be contained within a certain range of numbers.
Okay, so that puts a limit on how wild things can get. What about the lower bound, like the smallest the sumset could be?
That's where it gets a bit more complex. He uses these two key lemmas, which are kind of like special tools for his mathematical construction project.
Gotcha. So lemma 2.1 and lemma 2.2, I see them here in the paper.
Right. So lemma 2.1 basically provides a way to estimate the size of the sumset when you're dealing with a union of sets.
So like multiple sets all smooshed together.
Right, exactly. And lemma 2.2, it gives a condition for when adding two sets together will give you the maximum possible number of new sums.
Okay, so it's like telling you when those Lego blocks fit together in a way that makes the sum set explode.
Yeah, exactly. It's like if you have two sets and the differences between their elements never overlap, then boom, you get the most new sums possible when you add them together.
That's fascinating. So I'm starting to see how all these pieces fit together. He's building sets with very specific gaps between the numbers, using these lemmas to analyze how their sumsets behave, and then somehow all this leads to those flip-flopping sumsets. But like, how does he actually control the flip-flopping? How does he make the sumsets change order however he wants?
Well, that's where these special parameters come in. They're denoted as ani and li, and they basically act like fine-tuning knobs for the whole construction. He can tweak those parameters and make the sumsets do whatever he wants.
Wow, so it's like he's found the secret code for controlling these sumsets.
Exactly. And that's what we're going to dive into next. Okay, so remember those parameters we talked about, those any and Gauss values?
Those are like the secret ingredients in his recipe, right?
Exactly. They're like the key to the whole flip-flopping thing. So remember, we're trying to prove theorem 1.1.
The one that says we can find sets whose sumset sizes change order however we want as we add elements more times.
That's the one. So basically, we need to show that Kravitz can choose these parameters, the alphas and gammas, to make the sumset sizes like dance to our tune. We tell it what order we want, and boom, the sumsets obey.
Okay, sounds pretty powerful. So how does he actually demonstrate that? Where does he even start?
Well, it all comes down to proposition 2.4 in the paper. This proposition is like the heart of his argument. It shows that, given any set of permutations, we can always construct sets with parameters that make the sumset sizes line up in that order.
Okay, so proposition 2.4 is like the master key.
Yeah, pretty much. It's like the blueprint for building these like magical sets with flip-flopping sumsets.
Okay, cool. So walk me through this. Proposition 2.4, what's the logic there?
All right, so he starts by defining those Gauss values. Remember, those control the equivalence classes, right?
Right, they're like the categories of elements within each set.
Exactly. So he got like the gamma value for the arith permutation to be 10 and 10R.
Whoa, okay. Why that specific number? Seems kind of random.
It's not random at all. It's very carefully chosen to make sure that the scales introduced by those alpha parameters don't interfere with each other. Each alpha kind of scales a block within the set, and those gamma values need to be far apart to keep everything like separated and organized.
So it's like assigning different frequencies to radio stations so they don't overlap and create static.
Yeah, that's a great analogy. It's all about keeping those scales separate so we can control them individually.
Okay, that makes sense.
Yeah.
So what about the alpha parameters themselves? How does he pick those?
Well, he uses a clever construction based on like a generalized arithmetic progression.
So it's not just adding a constant number each time, like a regular arithmetic progression.
Right. It's a little more fancy than that. He takes a base value, which depends on the permutation and the set we're talking about, and then he adds multiples of those gamma values we talked about.
Oh, I see. So those alpha values are also spread out using those rapidly growing gamma values.
Exactly. And the spreading out is super important for creating the flip-flop behavior we want. By carefully choosing the base values and using those big gamma values, Kravitz makes sure the differences between the alpha values fall into very specific ranges.
And I'm guessing those ranges, they line up perfectly with those equivalence classes, like determined by the gamma values.
You got it. That's how he controls which elements end up in the same equivalence class, which, like we said, directly affects the sumset sizes.
Okay, so it's like he's weaving this intricate tapestry with the alpha and gamma values, controlling every detail of the pattern.
Beautiful analogy. They work together, like, perfectly to control the sumset sizes.
But how do we actually, tie those parameters to the sumset sizes. That's where the ERK values come in, right?
You're right on track. Remember, those ERK values represent the relative size of the HR-fold sumset of AC, that KRF set.
Yeah, but I'm still a bit fuzzy on how those ERK values connect to the alphas and gammas. Like, how do we actually calculate them?
That's the core of Proposition 2.4, showing you can express each ERK in terms of the alphas and gammas. It's like finding the perfect recipe.
So by tweaking the alphas and gammas, he's essentially manipulating those ERK values, which in turn dictates the order of those sumset sizes.
You're getting it. It's all about finding the right combination of ingredients to create the perfect mathematical dish.
This is starting to click for me. He sets up these parameters using those like crazy gamma values, which then lets him control the differences between the alphas. And somehow, this all leads to the ERK values being arranged just right to make the sumsets behave.
Yeah, you're seeing the big picture now. It's amazing how much thought and precision goes into this whole construction.
But to be honest, I'm still a bit unclear on what those ERK values actually represent. Like mathematically, they seem super important, but we haven't really dived into what they are.
Okay, yeah, you're right. We've been kind of dancing around their meaning. We need to break down those ERK values to really see how Proposition 2.4 works its magic. Remember, they capture the essence of the sumset sizes.
All right, let's do it. Let's get into the nitty-gritty math here. What's the actual formula, and how does it connect to all these carefully chosen alphas and gammas?
All right, buckle up. We're going deep.
All right, so we're finally ready to tackle those ERK values. I feel like we've been circling around them for a while now.
Yeah, they're kind of the linchpin of the whole proof, so it's time to see what's under the hood. Basically, ENRAK tells you about the relative size of the HR-fold sumset of set AC.
Okay, so it's like a measure of how big the sumset gets when you add the elements of AC to themselves, HR times.
Yeah.
But like, what's the actual formula? How do we calculate it?
Well, it all comes down to those equivalence classes, remember. Those are determined by the gamma values, and they group together elements based on their spacing.
Right. Those gamma values are like dividers, splitting the elements into different categories.
Exactly. Now, imagine you have a particular permutation like Wüster, and we want to calculate ERA. So first we look at the position of K within that permutation. Let's say Sur A equals K, meaning K is in the jth spot.
Okay, so we're figuring out where K sits in the order given by that permutation.
Right. Now here's where it gets kind of tricky. We need to count how many elements from the other sets, from A1 up to on, end up in the same equivalence class as the JF alpha value for AC.
Hold on, let me make sure I'm following. So we're looking at alpha J, the jth A alpha value for the set AC, and we're checking how many other alpha values from the other sets fall into the same equivalence class.
Exactly. But, and here's the kicker, we only count those alpha values whose index in the permutation surround comes before J. So like, if J is 5, we only count the alpha values for the elements that are in positions 1, 2, 3, and 4 in that permutation.
Okay, it's a very specific count. We're checking how the elements that come before K in the permutation relate to K's jth alpha value. But like, why is that so important? What does that tell us?
Well, that count, that's exactly ER. It tells you how much overlap there is between the set AC and the sets that come before it in the order given by SAR. And this overlap, it basically determines how big the HR fold sumset can be.
So if ERK is big, that means there's a lot of overlap.
Right, and more overlap means you're more likely to create the same sums multiple times, which limits the growth of the sumset.
So the sumset won't be as big if there's lots of overlap.
Exactly. But if ERK is small, it means there's less overlap. And that means you have more potential to generate new, unique sums, which makes the Ertar-Arfold sumset bigger.
Ah, I see. So ERK is like a measure of how much freshness you have when you're creating those sums. Like how likely you are to get new sums instead of just repeating the same ones over and over.
You got it. And it all comes back to those carefully chosen alpha and gamma values. By tweaking those parameters, Kravitz can directly control the ERK values, which then determines the order of those sumset sizes.
It's like he's playing this super intricate game, making sure all the pieces fall into place just right. Okay, so I think I finally understand what those ERK values represent. But how do they fit into the bigger picture? How do they actually help us prove Theorem 1.1 that we can create sets with any desired order of sumset sizes?
Okay, so remember lemma 2.3. That gives us a way to estimate the size of those H-fold sumsets. Well, when we apply lemma 2.3 to sets that are constructed using those special parameters from Proposition 2.4, something really cool happens.
What happens? Tell me.
The bounds on the sumset sizes, the ones we get from lemma 2.3, they turn out to be directly proportional to those ERK values.
So, like, the size of the sum set is basically controlled by those ERK values.
Exactly. And since we already showed in proposition 2.4 that we can choose parameters to make those ERK values have any order we want, well, that means we've basically proven theorem 1.1.
Whoa, okay, so it's like a chain reaction. Proposition 2.4 gives you the blueprint for the parameters, so the ERK values are all arranged correctly. And then lemma 2.3 connects those ERK values to the sumset sizes, guaranteeing that the sumsets behave exactly how we want.
That's it. You've nailed it. It's this beautiful, intricate construction where each part plays a crucial role.
Wow. It's amazing how much complexity can come from something as simple as adding numbers together. I mean, who would have thought that there's this whole hidden world of flip-flopping sumsets?
It's pretty mind-blowing, right? It really shows you the power of mathematical reasoning. Like, you start with a seemingly simple question, and it leads you to these really deep and surprising results.
Definitely. And I think we've reached the bottom of this deep dive. We've explored this whole world of iterated sumsets, unpacked Kravitz's proof, and even gotten a little taste of the broader field of additive number theory.
It's been a great journey, and I hope our listeners are leaving with a newfound appreciation for the beauty and, honestly, the weirdness of math.
Couldn't agree more. And remember, this is just the beginning. There's a whole universe of fascinating math out there just waiting to be explored. So until next time, keep those minds curious and keep asking those questions.